Hello everyone, welcome to the second part of your final exam review guide for historical geology. This is Dr. Hurt and this is the last video I'll be releasing, so you don't have to listen to any more of these after this one. So maybe you're happy about that, maybe you're sad about that, but in any case, we are finishing up today and we're going to go through questions number 51 to 100 and get you ready for your final exam, which is coming up very soon. I hope that you are steadily and speedily preparing for that, because it is coming. It is a doozy and you need to be ready because it is a pretty difficult exam. You know, it's covering the whole class from day one on, so you know, you're going to need to prepare for this one. So without further ado, I'll get on to this stuff. So talking about transgressions and regressions, what are those? Hopefully you remember a little bit about these. Transgressions, you know, we have, of course, the seafloor, and over the, you know, along with the seafloor, we have the continental crust, right? And there's your continental crust, and from time to time over Earth's history, the sea levels have risen and fallen. So sometimes they're relatively low, sometimes they are relatively high, and whoops, all disappeared. That's kind of weird. That is very strange. How does it, and why is it doing that? I do not know. That is so odd. I'm not sure what is going on with this thing. Huh. Okay. Very odd. I'm wondering if it's still... Huh. Okay. Whatever. I don't know what that's about. I'm going to try to start over here. But sea levels have risen and fallen over time. So transgression is when sea levels have risen, and a regression is when they have fallen. Okay, so that's all that is meant here. Now, an empiric sea is, again, you have the ocean floor, okay, and you have continental crust that is right here. It's thicker than the ocean crust, of course, and then you have your sea levels. And when sea levels are very high, sometimes you can see that they cover even the continental crust. So parts of the continent that are covered with ocean water create these relatively shallow seas. You can see that compared to where the ocean is over a ocean basin, ocean crust. This is relatively thick, deep compared to this, which is relatively shallow. Okay, so empiric seas are these shallow inland seas. Okay, and we see a lot of those in the Paleozoic. So what's the first supercontinent? When was it assembled? First one is Rodinia. Okay, Rodinia. And it was about 1.1 to 0.75 billion years ago is when we had Rodinia. Okay, how long do continents accrete together, generally speaking? So the process of continental accretion is that, let's say you have a, let me start over. Okay, let's say we start with a subduction zone. So here's, this is going to be an ocean subduction zone. So here's ocean crust, here's some more ocean crust, ocean lithosphere, it's going down, and remember that water gets released, right? So we have water here, it has seeped into the ocean crust, and that water gets released into the overlying mantle, okay? So this is mantle, this is O crust, the ocean crust, okay, this is O crust. Okay, that causes there to be volcanism, right? We have arc volcanism, okay? So basically we create these volcanic arcs, okay? So that creates the first kind of little speck of continental crust. Now, over time, what happens is that maybe another subduction zone forms over here, and we get another volcanic arc forming over here. Okay, and eventually that becomes continental crust, right? That becomes continental crust. But what's going to happen is, as this subducts, this old arc is going to collide with this new one, okay? And so you're going to get this buildup of continental crust. And eventually, from collision after collision after collision, we call that process accretion, okay? And so that's how continents, over time, they build up. And you know, these different volcanic arcs get glued together, and continents increase in size until they are, you know, what we have today. So what are the main orogenies of the Paleozoic in North America? So we had a few of them, right? Most in North America were mostly building up the Appalachians, right? So I can say that the Appalachian, we have a series of orogenies there, right? So we have the Caledonian, we have the Taconic, and the Alleghanian. Okay. We have the we also have the Ouachita. Okay, so we have a series of orogenies that occur over the period of the Paleozoic that involve various continents colliding with North America, which at that time was called Laurentia, right? So this is the Caledonians when Baltica is colliding with the Laurentia. Alleghanian is when we have Avalonia. Ouachita is when we have Gondwana, right? So these different continents or continental groups are colliding with North America, which at that time was called Laurasia or Laurentia, and that's what creates these various orogenies that are building up the Appalachians. Okay. What are some of the oceans present during the Paleozoic? So you should be familiar with the Panthalassic, and the Tethys. Tethys. Paleotethys, which came before the Tethys, and also the Rheic. Okay, those are all important seas. What are the main land masses present during the Paleozoic? You might remember Gondwana. Those are kind of the most important is Gondwana and Laurentia. Okay, which later becomes North America. Gondwana is really kind of the main chunk of Rodinia after Rodinia broke up, but it includes Africa, Australia, parts of what later eventually became Asia. Right, is all part of Gondwana. Laurentia is basically North America, and we also had other things. We had Baltica. We had Kazakhstania. Gosh, how do you spell that? Kazakhstan. Yeah. You had, what are other ones? China, actually, North China. Okay, so I've actually talked about 6 of them, but those are the main ones that Gondwana and Laurentia are really the main ones you want to remember that were present in the Paleozoic. So what is the Ediacaran fauna? So the Ediacaran fauna are the animals that were present in the Precambrian, before the Cambrian explosion. So they were rather mysterious. They're kind of difficult to fit into our current knowledge of phylogeny of the phyla, various phyla of animals, but they were mostly soft-bodied, perhaps some hard-bodied animals. It's very unclear. Kind of, mysterious, rare animals that are Precambrian, though. So that's what's kind of special about them. So what's the Cambrian explosion? This is something you definitely have to know about. I will be asking you questions about this. So the Cambrian explosion is 542 million years ago, and it is the sudden appearance of all of the major phyla of animals. Animals become all of a sudden very abundant over a period of about 10 million years. And there's a high degree of diversifying, and suddenly, you go from strata of rock that are virtually fossil-free to loaded with fossils of all sorts of things, arthropods, various mollusks, all sorts of marine life. Okay, so Cambrian explosion, extremely important event in Earth history. Okay, you definitely have to know about that one. You should also be familiar with that very important Burgess Shale, which we talked about, part of the Cambrian explosion. So what are cratonic sequences of the Paleozoic? So you might remember cratonic sequences are when you have you have a craton, okay, and you have an Epiric sea, okay. So the Epiric sea rises, there's a transgression, and you get this laying down of various sedimentary layers, okay. But then you'll get all these sedimentary layers laid on top of it, okay. So those are the cratonic sequences we see, and there are recorded about 5 different ones We have the Sauk, the Tipa canoe, right? We have in the we'll talk about the Mesozoic another time. We have also the gosh, why am I forgetting these ones? Sorry, I have to go remind myself some of these names. I'm forgetting them. Sorry, forgot the Koschia and the Absaroka. Okay, so these are the various cratonic sequences we experienced over the Paleozoic. So we had 4 major transgressions and regressions. And remember that between each transgression, between each of these cratonic sequences, the water levels will drop. Okay, let's say they drop down to this level, and you're going to get, basically, I could even kind of erase some of this stuff, right? You're going to get a erosion of those surfaces, right? So you get an unconformity here. Okay, you get unconformities. And then when the sea levels rise again, let's say sea levels will rise like that, you get new sedimentary rocks laid down. Okay, and there'll be unconformities between the old sequences. Okay, so anyway, that's just real quick breakdown of cratonic sequences in the Paleozoic. So I just explained what a cratonic sequence is above, so we finished that. What kind of rocks are laid down during these sequences? So they're going to be shallow, right? Various shallow marine sorts of things. And remember how it goes is that, I want to show you this, it's very important. So when you have water levels like this, okay, so near the coastline, what kind of sediment do you get laid down? I'm sure you're all familiar that you get sand laid down near the coast, okay? So there's sand. So a lot of times we're going to see sandstone laid down first during a transgression, so we'll get sandstone. Okay. Now, as water levels rise, see in deeper water, then we start to get clays and shales laid down out here. Okay, because sediment always gets finer and finer and finer as you move out further and further away from the shoreline. Okay, so then you get clays laid down, so you'll get shales on top of the sandstone. And then finally, when you get into real deep water, there you get, coral reefs. I'm trying to draw like corals and coral reefs, okay? You get coral reefs, and you start to lay down limestone there, okay? So then you'll have another layer on top of this that will be limestone, okay? So I hope you remember your rock symbols. That's the limestone symbol, okay? So limestone. All right, so when you see a sandstone, shale, limestone, that's a classic. You probably remember the sandstone, shale, carbonate assemblages. It's a transgressive sequence, okay? If it's flipped on its head, so it's limestone, shale, sandstone, then that's a regressive sequence. It means water levels were falling in that area. What reef-building species were prevalent during the Paleozoic? You might remember the stromatoporites. Okay, stromatoporites, which are a type of sponge. Okay, these were porifera sponges. Okay, generally you should have some good ideas about what kind of animals, plants were common during each era of the Phanerozoic. So I'm going to show you some pictures, scenes of each era, and in some cases maybe even specific periods, and you need to be able to distinguish what they're talking about. So this is what we're going to do. I'm going to have pictures of from kind of early Paleozoic. I'm going to have one late Paleozoic. I'm going to have one of Mesozoic, and then one of Cenozoic. And you need to be able to tell the difference between all of these ones. So kind of a dead giveaway for early Paleozoic. It's going to be only marine life. Okay, there's not going to be any continental life, right? When we start getting continental terrestrial life, that's in the later Paleozoic, and Carboniferous, Devonian, things like that. Maybe you'll start to see in the late Paleozoic, maybe we'll start to see swamps and trees, gymnosperm trees, ferns. Maybe you'll see in the late Paleozoic, you could even see in the Permian early reptiles, amphibians, things like that. In the Mesozoic, you're looking, of course, for dinosaurs. Cenozoic, you're looking mostly for mammals. So it should be pretty easy. But, definitely you should be able to tell the difference between looking at the fauna, the animals, and the flora, the plants, be able to get a good idea of what age we're talking about. Okay. I might even go and do this again, showing you just fossils. I'll show you a fossil assemblage, and you'll have to tell me, not just like a nice pretty artist scene, but a fossil assemblage. You'll have to tell me what era you think this represents. And again, you're just looking for those kind of key things. You're looking for like mammals in the Cenozoic, dinosaurs in the Mesozoic. You're looking maybe for early amphibians, early primitive reptiles in the late Paleozoic, early Paleozoic. Maybe you're looking for graptolites, bryozoans, corals. What else? Trilobites, things like that. Okay. So anyway, that's how you would do an exercise like that. You should have some grasp about tetrapod evolution. So the different groups of fish, you might remember ray-finned fish, cartilaginous fish, lobe-finned fish. Remember that lobe-finned fish gave rise to the first amphibians. Amphibians eventually gave rise to reptiles. You should remember some examples of early reptile or early amphibians. For example, Ichthyostega, Canthostega, right? You should remember species like that, specific species. So there'll be some questions, or a question, I should say, about early tetrapod evolution. Okay. What are some of the earliest amphibian species? I just mentioned them there, Canthostega and Ichthyostega. There's also Tiktaalik rosea. It's kind of a weird. Tiktaalik. This is actually a species from Greenland, so it's like an indigenous language, like native, like Inuit word. So that's why it's kind of a weird word. But Tiktaalik rosea. Okay, those were all early, early amphibians. Canthostega. Sorry if you can't read my handwriting. I'm trying to go fast. Anyway, what's the difference between a reptile and an amphibian? So the main thing here is, there's a lot of differences, but the main thing is amniote. Okay, so reptiles are amniotes, amphibians are not. You should know what an amniote is. Okay, what are some specific species of early reptiles? Okay, so some of the early reptiles that we talked about. Gosh, I have to think about them. There's quite a. Well, I don't know. We didn't talk about so many, but you should remember the what was that group? Well, there's a whole group. You might remember the protothyrids, and some of the examples of that are like Archaeothyrus. Whoops, Thyrus. There we go. And gosh, I'm trying to remember the West Lithuania. Those were the two that I think I mentioned, if I recall in a lecture. So, but probably be good. Probably if you just know a little bit about protothyrids, and just how they were different than the amphibians. Because remember, basically what's going on at this time is that we see amphibians trying to dominate and take over in terrestrial environments and get away from the water, right? So there are these changes that were occurring to help them adapt to life away from the water. Okay, so we see things like, of course, amniotic eggs. So that allowed reproduction to occur outside of an aqueous environment. We see the advent of scales and tough skin that helps it to avoid desiccation. we see the advent of a more developed respiratory system that allows them to get oxygen from the air without water. So there's a lot of different things that are going on that differentiate protothyrids, early reptiles, away from amphibians. So just some general, familiarity with that whole process is going to help you on the test. So when did the first land plants evolve? So we did have land plants as early as the Ordovician. So that remember Ordovician is very early on, right? Cambrian, Ordovician, Silurian, Devonian. So by Ordovician we do have some land plants. But remember that early land plants were non-vascular. Things like mosses and liverworts, hornworts, things like that. Okay. Some early kind of vascular plants were things like ferns, like you might remember Cookstonia. It's a type of fern. Early fern had spores, reproduced with spores. So we didn't have seeds at this time, right? Gymnosperms had seeds. Angiosperms obviously have seeds. But anyway, hopefully you can remember some of those initial land plants. By the Carboniferous, we see very extensive forests. Even by the Devonian, we start to see very extensive forests forming. You might remember the Lycanopterids. I can put that down here. Okay. These early trees, kind of like fern trees, dominating the forests of the Devonian, and by the Carboniferous, forests were very extensive. Okay, so but we do see as early as Ordovician we start to get fossils of non-vascular plants on land. Okay, what is significant about therapsids? This is something you really have to know about. Therapsids are the early, you might remember the synapsid line, right, gave way to the therapsids. These are early reptiles that are, I shouldn't say early reptiles, they are reptiles that are eventually going to give way to the mammals. So it's the group of reptiles that splits off from remember there's a split, synapsids and diapsids. And we see that split. Diapsids eventually give us the dinosaurs. Therapsids give us mammals. Okay. Now you should be able to distinguish a reptile diapsid skull from a therapsid. There are a few ways that you're going to do that. So a synapsid, I'm going to kind of try to draw this for you here. Okay, so I'm going to draw a synapsid skull. Okay, so we have the orbit, right, for the eyes in a synapsid. And we see, with the synapsid, we see one fenestra behind the orbit, okay? Now, another thing that might differentiate it is that we're going to see some differentiation in the teeth, okay? So we're going to see some teeth that are different. Maybe we'll see a canine here like that. So that would be maybe a therapsid. Now, a diapsid, which is more of a reptilian, dinosaur-type skull, every tooth is about more or less the same. Okay, so we don't see much differentiation in teeth. Okay, now we have the orbit here for the eyes, but we see with diapsids we see two fenestrae behind the orbit. Okay, so that's what a diapsid reptilian skull is going to look like. Okay, so that's how you would know. Kind of just making this look better here. Trying to make it look better. Kind of ashamed at how badly this turned out, but it's okay. But that's more or less. You're just looking for those number of openings. That's how you'll tell a difference between, and the teeth. That's how you'll tell the difference between diapsids and synapsids. And of course, synapsids give way. Therapsids are in the synapsid line. Okay. Now, what percentage of marine species died out during the PT mass extinction? It was about 95%. Okay, what was the single large landmass that assembled at the end of the Paleozoic? That was Pangaea, right? Supercontinent, when did the supercontinent start to rift apart? That was during the Jurassic. Whoops. Okay. What are the Hudson Palisades? When did they form? So they formed in the Jurassic, right? And they were, when they're in Hudson, Hudson River, New York City. So they are very close to, they're on the border of New York City, right? So the Hudson Palisades. And basically they're these very, very steep basalt cliffs that were representative of huge pools, at one time huge pools, lakes of basalt that formed as Pangea began to rift apart in the Jurassic, early Jurassic, okay? So what are some of the principal orogenies of the Mesozoic in North America? So now we're getting into Mesozoic geology. So we talked about a few things, but now we're seeing the West Coast start to become tectonically active instead of the East Coast. Remember, all the tectonics were happening on our East Coast in the Appalachians during the Paleozoic. Now during the Mesozoic, we start to see the Cordilleran orogenies take over. So the Cordilleran is split into a few things. So we get the Nevadan, the Sevier, and the Laramide. Okay, those were the main orogenies that built up the Cordilleran in North America. So for example, the Rocky Mountains were built up mostly during these Sevier and Laramide orogenies. Now, what's the difference between Sevier and Laramide orogenies? So Laramide came after the Sevier, but one thing that characterizes them, and they're different, is that Sevier is more to the west. Laramide was very deep inland, so it was far to the east. Okay, which is unusual because you would expect a subduction zone. Remember that the Farallon plate was subducting along the west coast of America at this time. So, well, not America, but North America, the continent of North America, I mean. So you would expect mountains to get, right, you have a subduction zone. Okay, here's the Farallon plate going beneath. Let me erase some of this junk on here. Okay. I'm going to draw North America. And here I'm going to draw the Farallon plate subducting. Okay, so here's the subduction of the Farallon plate. Now, that builds up, starts to build up the Sevier orogenies. Okay, and then after that, what happens is we get flat subduction. And a lot of that stress gets forced to the further out to the this is the west, this is the east, further out east, and you get the buildup of the Colorado Plateau and the Rocky Mountains with the Laramide. Okay, because we underwent flat subduction during this time of the Farallon plate. Okay, when was the Sierra Nevada batholith in place? That was about the Cretaceous times, Cretaceous, and late Jurassic. Okay, that was because remember during the subduction of the Farallon, right? This is introducing all this water into the mantle. It's causing partial melting of the mantle. So you're getting a lot of these melts, and some of them are just not getting erupted, but they're just getting emplaced, and you get these massive magma chambers that are in place. So Sierra Nevada batholiths are in place during the time of the Sevier orogeny in the Mesozoic. Okay. Now, what's the basin and range province, and why, when did it form? So, again, remember that we have, again, I'm going to draw out North America. Okay, so here's, and we had subduction of the Farallon. Okay, I'm going to draw this flat subduction. But, at some point, the Farallon peters out, right? It's subducted, the ocean crust is totally gone. And so we have this compression, and we have mountain building for so long, creating the Sevier orogenies and Laramide orogenies, lifting up the Colorado Plateau and the Rocky Mountains. Okay, and we get all this compression, but then eventually, it stops. Okay, it stops. So we don't have the Farallon plate subducting anymore. Okay, well, we do sort of, but not over the entire margin there. So there's a little bit of the Farallon plate left in the Pacific Northwest, but mostly it stops, okay? So once that, we have these big compressive forces that all of a sudden stop, okay? And when they stop, what happens is this is getting all scrunched up, and it wants to kind of relax back out. And when it relaxes, you get these kind of normal faults. Okay. And what happens is I'm going to kind of redraw this stuff here. Whoops. But you get these normal faults. That thin out and extend the crust. Okay. So you get this series of basins, what are called basins and ranges. So you get a basin, you get a mountain range with a basin, and then a mountain range and a basin, and a mountain range and a basin. So this creates the basin and range province. Okay, so this happens actually getting into the Cenozoic after compression from subduction of the Farallon plate comes to an end at the end of the Laramide orogeny. Okay, so how did marine ecosystems change after the KT mass extinction? So KT mass extinction, remember, is the end of, the K stands for Cretaceous. Okay, just go with me here. I know Cretaceous stands with a C, but starts with a C, but it's this. The old term for the Cenozoic, the first period of the Cenozoic, used to be called the Tertiary. We don't call it the Tertiary anymore, but that's where the T comes from. So this is basically the end of the Mesozoic, beginning of the Cenozoic mass extinction. So a lot of things went extinct, right? Marine reptiles went out. Okay, they're gone. Rudist. Remember those guys, the rudists? Okay, they're bivalves that were basically took over all the reefs. Rudists are out. So all the marine reptiles, by the way, those are things like I shouldn't say all of them, but a lot of them. Ichthyosaurs, mosasaurs, plesiosaurs, they all go extinct. Okay, rudists go extinct. Lots of changes to the plankton. Okay, planktonic environments really change. So we see kind of moving away. We see extinctions in a lot of the main groups of the planktonic phytoplankton species. So foraminifera, coccolithophores, radiolarians, diatoms, dinoflagellates. They all kind of take a big hit, but they bounce back. But radiolarians especially become very popular, and also diatoms. So remember that diatoms really bounced back in the Cenozoic. That's what creates that. You might have heard that material's diatomaceous earth. Okay, it's from the diatoms that die and sink to the ocean floor and create that special kind of sediment. So speaking of KT mass extinction, when was that? Oh my gosh, you got to know this. Okay, 66 million years ago. Definitely got to know that. What event caused it? It was that meteor strike. How do we know it? There's a lot of evidence for this. Some of it comes from iridium levels in the KT clay layers, so the barrier clay layer between the Cretaceous and Tertiary. We also see what are called microtectites, which are little glass spheres. Okay, little glass nodules, very small. You can only really see them with a microscope. They're little glass spheres that represent basically melted rock that were thrown up into the atmosphere as an aerosol after the massive meteor impact. So the meteor impact created so much energy, it melted the rock, turned it into these fine droplets of melted rock that crystallized, became little tiny sphericals of glass that eventually fell back to Earth over the entire surface of the Earth and creates this kind of material called microtectites. We also see wood ash from like global wildfires during this time. So a lot of interesting things we find. The iridium, though, is the thing that really, I shouldn't put IR. It's iridium is actually I lowercase r like that, not I with a big R. So that's the iridium layer there in the KT clay is very indicative of a meteorite impact. So what orogenies are currently, so now we're moving into the Cenozoic. What orogenies are currently underway on Earth? So we have right now the Himalayas. And we have the Cascades, which are part of, the Cascades are all part of the greater, I guess I can call it the Circum-Pacific mountain range. We call it Circum-Pacific mountain range because it's really one continuous mountain range that goes, you know, all across the Pacific because the Pacific is basically subducting. Almost the entire thing is subducting. So, you know, we get the Cascades, we get the Andes, the Sierra Madres in Mexico, the Aleutians, Japan. You know, it's just there's so many mountain ranges that are part of this larger Circum-Pacific mountain range. Even the Himalayas are really kind of one continuous mountain range, along with the Alps in Europe. So anyway, but Himalayas and Circum-Pacific are really what you want to know there. So how is the climate change over the course of the Cenozoic in North America? So really we are going from a hot, humid, kind of like a hothouse environment that was very common during the Mesozoic and into the Paleogene. Remember the first period of the Cenozoic. But then things after the Paleogene, after the Eocene optimum, that's the high temperature optimum that reached in the Eocene, right? So it's the end of the Paleogene. Temperatures start to cool down, and we get this expansive period of cooling and drying moving into the Pleistocene and into today. Okay, so things are becoming cooler and drier during the Cenozoic, especially after the Paleogene is finished. Okay, now you should be able to understand and explain how we know about climates of the past using fossil leaves and oxygen isotopes. Okay, so remember that from fossil leaves there's leaf margins. Okay, so remember that leaves that have kind of serrated margins like that, those are more indicative of kind of like a cold environment. Whereas if you have leaf margins that are nice and smooth like that, that's more indicative of a hot environment. Okay. Now another thing is oxygen isotopes. So we can look at fossil leaves and kind of figure out what the climate was like from fossil leaves. To get kind of a more, I can say, maybe the good word for it is a quantitative sort of measure of temperatures. We can also look at oxygen isotopes. So just this is kind of a difficult thing to talk about very quickly, but okay, here's a continent, here's an ocean basin, here's the ocean, okay? And what I'm going to do is I'm going to draw a glacier here, okay? It's a glacier. Okay, there's your glacier. So the thing is that we have two types of oxygen in the water. Well, actually we have three types, but let's just talk about these two types. So we have oxygen 16, oxygen 18. Okay. So now the thing is that let's say I'm going to draw a few oxygen 16s. Okay. So let's say there's, for every oxygen 18, there are 3 oxygen 16s. Okay. So this is the thing, is that oxygen 16, because it has less neutrons, it likes to kind of, what can I say? When you have H2O made up out of oxygen 16, that H2O is going to, the oxygen 16 H2O, so we'll call H2O with a little 16 there, likes to evaporate more than the oxygen 18. Okay? Now, if it just goes up into the clouds, now most of the time it just rains, you know, and that oxygen 16 gets returned back to the ocean. But if it is cold, okay, folks, if it's cold, sometimes that oxygen 16 can go and get stored in a glacier. And then the glaciers become rich in oxygen 16. And some of the oxygen 16 gets pulled out of the water, and it makes the oxygen 18 ratio higher. So oxygen 18 increases in abundance in the oceans when there is a lot of glacial ice present on land. Okay, so the story is this: if oxygen 18 levels increase in the ocean water, it's showing that temperatures are becoming colder. There's more ice, there's more glaciers, okay? So that's another way that we know, through this record of oxygen 16, oxygen 18, we know what the temperature was like, or we think we know at least. So can you please explain how oxygen isotopes tell us about Earth's climate? We already do that. We already did that above. Can you mention some differences between the severe and laramide orogenies? Actually, I don't even know what this question is doing there. We already talked about this. So the laramide is, actually, you know what? I didn't talk about this in entirety. So the laramide is more, of course, I said, to the east than the severe, which is out to the west. But another thing I want to talk about is that severe, okay, so the kind of mountain building that we see from the severe, it's more sort of like thin-skinned, fold thrust belts like this. Okay. So I'm trying to draw this kind of like folds of sedimentary rocks sitting on top of the craton. Okay. So that's kind of like severe style mountains. You get these fold thrust belts of the sedimentary rocks sitting on top of the craton, and that's what's building up the mountains, is this folding, okay? But in the laramide style, what we see are these very deep faults that go deep into the craton that are just kind of lifting up the sedimentary rocks and also portions of the craton as well. And so we get these very deep faults that are going all the way through the cratonic, the cratonic rocks, not all the way through, but even into the cratonic rocks, and we see this uplift. And these are very, very vertical type of, like very high angle faults, okay? So anyway, that's kind of the difference in styles between the laramide and the severe. Now, can you explain how flat subduction of the Farallon Plate during the Cenozoic resulted in mountain building 1,000 miles inland from the subduction trench? Again, it was because you had this flat subduction. It kind of transferred the stress away from the east coast, or away from the west coast, away from the subduction zone, and 1,000 miles inland. Okay, so normally, right, this thing would just subduct right here on the coast, but instead, it got buoyed up by probably a rising plume, and it transferred that stress inland into the east and lifted up the Rocky Mountains. And that's why it's weird, because we have the Rocky Mountains kind of like in the middle of our continent, and that's a little bit strange, okay? Normally we get these mountains being built up along the coastlines, like in the Andes Mountains, for instance. Okay, what are some hypotheses about the flat subduction occurred? Why do we think flat subduction occurred? It's because we think perhaps there was so here's the Farallon Plate kind of going down beneath North America, okay? Here's America. Here's the Farallon Plate, and then you get the flat subduction, and then it goes down. We think possibly that because there's so much hot plume activity going on, that this hot plume of rising material was kind of buoying up the descending plate. So it was keeping it from going down, and that possibly is what created this period of flat subduction. Okay, this question, I already asked this question. I don't know what this is doing here. What major group of Mesozoic marine reptiles went extinct? So we had the ichthyosaurs, the mosasaurs, and the plesiosaurs all go extinct during the Mesozoic, the KT mass extinction. What species now dominate reefs in the Cenozoic? Those are the it's hard to the scleractinians. I'm gonna try to scleractinians. Okay, don't quote me on the spelling. I'm gonna put spelling. I think that's how you spell it. Scleractinians. Okay. Somebody's gonna have to Google that and see if I spelled it the right way. But the scleractinians, though, are a group of, again, these are corals. Okay, so they belong to Cnidaria. The scleractinians have kind of hexagonal kind of trying to draw the hexagonal shape that you see with these things. But they have these kind of hexagonal, almost like honeycomb type of distribution in the what are called the columna, like the different sort of little apartments that the zooid animal lives in. And you see these what are called radial septa. So these septa separating each columna kind of look like this. Okay, they're surrounding it radially. Okay, so that's just, I'm just kind of trying to draw for you the morphology of these things so that you could, you know, identify them in a picture. Okay, so that's the Scleractinian fossil. So that's why people, you know, the coral reefs, we call them coral reefs for a reason, because reefs nowadays are dominated by corals, especially Scleractinian corals. But it didn't always used to be the case, right? In the Mesozoic, they were dominated by bivalves, right, which are types of, in the same family as clams. Okay, so the rudists, right? Moving on to more Cenozoic life. So what are the ungulates? Okay, what are two major groups of ungulates? Remember, we have the perissodactyls and the iridiodactyls. Whoops, dactyls. Yeah, like that. Okay, so these are the odd and even-toed ungulates, right? So this is, I think, I have to also explain what ungulates are. So ungulates are, those are like our four-legged, hoofed, usually hoofed mammals that are running across the savannas and across the grasslands. So this became a very important group of mammals as we moved away from kind of heavily forested, kind of like rainforest type ecosystems in the Eocene, the Paleogene, and started to transition into more like grasslands during the Neogene and the Quaternary. Okay, so we got the ungulates becoming kind of like fast, large-bodied land mammals that were well adapted for life on the grasslands and the savannas. Okay, and there's always this evolutionary trend towards less and fewer toes. Okay, so you see that in horses, where horses are very well adapted to grasslands like that, and they have only one toe left, right? So the hoof of the kind of the leg, the hoof of a horse is actually just one large toe. So it's kind of a funny way to think of it, but it's true. Okay, angiosperms and gymnosperms. You know we had to get around to this eventually here. So angiosperms are flowering plants. Flowering could be trees or any kind of flowering plant that has fruit and flowers. Gymnosperms, on the other hand, are things like conifers, cycads, also ginkgos. There's also one species called Velvetia that's a gymnosperm. These are the group of plants that do not produce a flower, okay, but they do have seeds. So they're seeding plants without flowers, okay? So what are some plants that are angiosperms? What are some that are gymnosperms? So angiosperms are any kind of fruit, grass, cactus, anything with a flower and a fruit. Okay, gymnosperms are conifers, cycads, ginkgos. For the most part, that's what it consists of. Okay. Now, is grass angiosperm or gymnosperm? It's an angiosperm. And that's important because that's part of the reason that grasses didn't, grasslands, these vast savannas and grasslands didn't take over until the Cenozoic, is because it was kind of a later advance. Grass came a little bit later. Okay, trees came before grasses. Why didn't placental mammals catch on in Australia? It's because in Australia broke off before the evolution of the placenta. Okay. So that's why Australia is dominated by marsupials. You should also be able to distinguish the differences. So getting on to human evolution, you should be able to distinguish differences between ape, Australopithecines, human skeletons and skulls, hominids. This should say hominid instead of ape. Okay. So how do you tell the difference? Well, apes are going to have, if I was to draw a chimp skull, I can kind of draw, let me draw some of these things out. So first, a chimp is going to have a very small brain case. Chimp will have a sagittal crest on top of the brain case. That's for the jaw muscles to attach. Have very big cheekbones here, so to allow the expansive jaw muscles to fit in there. Okay, you're going to see no forehead in a chimp, and this is a side view, by the way. And then you'll see a pretty, you know, long snout. Okay, so there's your chimp skull. Maybe I made it kind of too long, but that's kind of more or less what a chimp skull looks like. Okay, now a hominid like an Australopithecus, let's take that. You're going to see a larger brain case. You're not going to see a sagittal crest though, because most hominids didn't need to have that extra surface to attach jaw muscles. Jaw muscles just weren't as important. You'll see a little bit of a forehead, but not too much, and then you get a big brow. But this is the thing, a big difference between chimps and Australopithecines is that you have a much flatter face. Okay, so now you get a little bit of a jutting profile, but not very much. Okay, so there you go. And you get relatively big cheekbones still. So there's your kind of a hominid skull, okay? And now with Homo sapiens, of course, you're going to get a large brain case, very large. You're going to get a forehead, okay? So you see that there's some space there. And you get a more or less totally flat face with no big eyebrow ridge, okay? I mean, I'm kind of assuming you know what human skulls look like, but okay. So that's more of a human skull, okay? So anyway, it shouldn't be too hard, but you should be able to tell a difference between hominids, chimps, apes. Maybe I'll throw Homo erectus in there as well. Maybe Neanderthalensis, but you should just kind of familiarize yourself with some of these differences you're going to see. Okay, so major difference between Australopithecus and Homo genus. Okay, so the Homo, which includes Homo habilis, Homo erectus, Homo sapiens, Homo neanderthalensis, those are the ones I talked about. We're going to have larger brain cases. Going to be smarter creatures. We're going to walk completely and totally upright, which is, Australopithecines still had a little bit of hints of kind of a bent back and things like that. So hominids are going to be totally, not Australopithecines were hominids, but Homo genus is going to be totally upright. They're going to be tool makers. They're going to be more intelligent. They're going to have hands that are more adept for tool making and for dexterity. Okay. How old are the earliest hominid fossils? The earliest one is 7 million years. Okay, that's not Homo genus, that's hominids. So remember the Sahelanthropus chadensis. Remember, it's 7 million years. Ardipithecus and Kadaba and Ardipithecus. What's the other one? Can't remember. Ramadensis are more like 6 million years old. Okay, there's also Orinin tugensis, which is around 6 million years old. But the earliest one is Sahelanthropus chadensis, which is 7 million years. Okay, earliest fossils of the genus Homo. So that was maybe only we're getting to maybe like 2 million years ago. You start to see Homo habilis. 1.8 million years ago, start seeing Homo erectus. Okay, what are the earliest fossils of Homo sapiens? Those are around 160,000 years ago. Okay, not millions of years ago, only 160,000 years ago we get the earliest Homo sapiens. Key species of the Homo genus, I mentioned them. You have Homo habilis, Homo erectus, Homo neanderthalensis, and of course us, Homo sapiens. Okay. And then what are some key differences between them? Homo habilis was a relatively small creature. kind of similar in size to Australopithecines. But the big thing is that he was a tool maker, okay, or he or she was a tool maker, okay. Homo erectus was different than Homo habilis because it was larger. It was had a larger brain case, a flatter face, and also made much more adept tools. Okay, Neanderthals were, so Homo neanderthalensis was again a even larger creature than Homo erectus. Even in some cases, maybe even not as tall as Homo sapiens. We're the tallest of these, the Homo genus, but they were very large-bodied and larger than Homo erectus, and again, very, very intelligent. I mean, probably for all intents and purposes, basically human-like in their intelligence. And of course, Homo sapiens, I think you realize the differences between them. So anyway, those are all the things that you need to know about for the test, right? So I kind of gave you a quick breakdown. Now, just to kind of give you an outlook of things, you know, if you just watched the videos and you did your study guides, you know, and you completed, you should not just listen to this, but you should go and write out answers to everything. And write it out completely, write it out fully. Okay, I'm just kind of like, you know, I was just kind of putting down notes here, you know. But you should actually write these things out fully, make sure that you understand them. And, you know, I think if you do that, you should be pretty well prepared for the test. But if you want to be sure that you're going to get an A or a B, you know, you should go the extra step of making flashcards, doing your reading, you know, reading the textbook. Like I said, I didn't emphasize very much in this class, but it's a good thing to do to help retain this information. And anyway, also reviewing your old lecture assignments, very good preparation. Okay, so that's it. With that, I will say adieu and good luck preparing for your test, and I wish you all the best. And I really, really hope that you study hard, because I want to give as many people A's as I possibly can. Okay, so please reach out to me. Let me know if you have any questions about the test, you know, anything else. So I'm here to help you be successful. So reach out to me if you have any questions. So with that, it was a pleasure teaching you all, and I hope that you learned something you consider valuable in this class. And I really do wish you all the best. Please let me know if you have any questions or help. And I hope to see you someday on campus. If not, have a you know, good luck in your classes, good luck on your finals, and wish you all the best.